December 24th, 2015. You're looking at the beam setup page this afternoon at CERN. You're running lead collisions now. Notice the PB82, that's the symbol for lead. Notice it's down, they've downstepped this to 6.36 TeV per beam. There's a reason for that. There's more energy involved when you're dealing with lead ion collisions than with proton to proton. And here's what they're saying. With the proton run at 13 teraelectron volts now over for 2015, preparations are in full swing for the LHC to investigate lead ions, as it does for part of each year. But first, the operation team has been colliding the protons at lower energies than usual to provide a baseline for the lead run. And we've seen that back and forth over the past week. Collisions between lead ions are much more complex than those between single protons. Let me say this. They say they did this after each run back in the different years, but never at this energy. When lead ions collide at energies of several TeV, the extreme conditions give rise to a hot, dense soup of particles known as quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Experiments at CERN study this plasma to gain insights into the nature of the early universe. It says to cut through the complexity of the lead fireball, the CERN physicists will compare their lead-lead collision data with that of the proton-proton and proton-lead collisions. Here's why they're turning it down. The lead nucleus in the LHC has 82 times the energy of a proton, and that's why they're having to back this thing down. You can pause this and read any of it if you want to go into the details any further, but it's saying that for the collisions between the lead ions, they're going to reduce the LHC's magnetic field a little from the levels corresponding to proton energy at 6.5 TeV to 6.37, because that gives us the same center of mass energy of 5.0 TeV per nucleon pair as we had in 2013. At that time, though, they were colliding 4 TeV protons with lead ions. This is higher energy, and it's going to be lead to lead. It says the proton-proton reference data being taken in this past week, it was running at 2.5 TeV. Many of you saw that. Very low energy, had very little effect on our magnetosphere at all. They're saying finally the experiments will be able to make precise comparisons among the data. And what they've done is figure out how to have the same energy level depending on the different elements that they're colliding as far as these two. You're looking at both beams running again. Notice the timestamp 19, 18. They are 6 hours ahead of the East Coast here in the USA. So that gives you a time reference. They do not use UTC time, they're Swiss time. Now notice on this coordination planning page that it has not been updated since Monday morning, but that's when they started setting up the ion cycle with the ions. And like I said, I was watching the first time and they had to dump the beams and to go back in and do something. If you look at the different pages and the different experiments going on, you can see since yesterday they've been running through this cycle. When they get this thing up at, again, the full power and maintain it, we may see a lot of things change. Again, you're seeing that they're in the middle of the collisions, and we'll be keeping a close eye on this. Briefly, remember the coronal mass ejection from a few days ago? This is the Enlil tracker, and you can see that impact would be, even at a glancing blow, on the 25th at noon. Now, that would be UTC time, so that's going to put it close to 6 a.m. tomorrow morning on the East Coast. Also designated in the airs with the location of stereo A and B in the blue and red block on the opposite side of the sun. Had that question in from the last video. Solar activity has been quiet since that CME. You've got a few sunspots there that are very moderate, are registering very moderate flares. Have a small filament released this morning, and I'll show it to you on that camera. Notice right there, guys, is when they release that energy as it collapses back to the solar surface, creates a secondary flare called a Hyder flare. Now, Comet Catalina, it's an interesting animal because it just came through the ecliptic. It came around the sun, and it comes up between the orbit of Earth and Mercury. Now, it's on the other side of the sun from us now, but people from around the world are starting to get some good pictures of this comet. Check this out. It's from Arizona, different places. Now, this is one of the better ones. It shows both tails. One tail is more or less the debris trail. The other one is the ion trail out to the right, guys. And that's telling you the direction from the sun, because that solar wind is blowing past that comet, regardless of the forward direction of it. This is a close-up, and I can tell you that it survived that perihelion with the sun quite well. Of course, it wasn't very close because the nuclei is intact. Again, a couple of other pictures from this. They discovered it 2013, but guys, they don't know how long the orbit is, even though they've had that many days to check this thing out. This is from Payson, Arizona, Chris Scherr on November 22nd. Payson's a beautiful place. I've been through there going to Sedona. The skies are unbelievably clear. Now, if you look at the JPL of Catalina, it's called C2013 US 10. It came from below the ecliptic of the inner solar system. It goes much further out than Jupiter or any of our planets. That's when they're not sure when it's going to return. They call it a hyperbolic comet. But when those blue lines change color in this orbit, that's the point where it crosses the ecliptic of our solar system. See that? We're right now, it just came from below us in the dark blue lines. And as I progress this forward, you will see it start to rise. It goes through into January. So for the next few months, there may be some very good pictures of Catalina. Very interesting, because when they discovered it, they had never seen it before, or either this, because it's hyperbolic, it had been so long since it came into our inner solar system. It just lets you know, as you look at these charts, how little we do know about God's creation. But on the orbital element page, you can see they've orbited. They had a data arc span back to from 08-2013 on the 14th. But if you look at the period, which is in the left column, it says NA on the date and year. They do not know when this thing will return or when the last time it was here. Now, we'll say this, is it came in between the orbits of our planet and Mercury. It left a small debris field. Now, will we see that as we come back around next year and cross through the path of that? As far as meteorites, it'll be interesting to see. But we're keeping an eye on this and many other things, guys. It's a heads up. Be safe.